Okay, so let's see what you said. What's the probability? It is equal to 0. And again, once again, I have lost my mouse. So this is the issue we're dealing with this morning. It is hiding on one of the screens. Okay, do I have it? Is it there? I see a mouse. Okay, amazing. Okay. What did people say? Let's find out. Reveal counts. Okay. Lots of things that are all over the place. 13 people said 0. This was exactly the trap I wanted you to fall into. So ha ha ha, if you fell into my trap. Why is this a trap? Because in the simulation, there were 0. So if you are a little bit mixed up on what the question is asking, if you had the right answer to the wrong question, you will read off, you'll say, hey, there were 0 things at 0. There were also 0 things at 10. So the probability is 0. But that's not right. What? Does anyone know why that's not right? Can you read off the probabilities from the 800 and whatever, 26 simulations we did? Or not? Some people are shaking their head. Yeah, how would you, suppose someone says, look, it's 0. What would you tell them? Why is that not right? Yeah. Yes, exactly, yes. So 800, that's a great way to say it. 826 seems like a lot of samples, but the number of samples you do will never be enough to get the exact answer to the question. So in other words, these samples, sort of as you increase the sample size, will get closer and closer to approximating the true actual distribution, but they will only ever get closer and closer to it. They will never actually reach it. So if you want to know the exact answer, you cannot do it just by sampling. You have to do it by calculating. Another way to say that is this is the experimental probabilities, the probabilities in our experiment, and because our experiment has a limited sample size, it doesn't give you the true probabilities. That's a really excellent way to phrase the idea here. Another extreme example you can imagine only one ball was dropped. Then all of the probabilities would be 0, except for a single one of them would be 100%. Of course, that can't possibly be correct. So you can also think about it that way. But that is a common misunderstanding, mixing up sort of theoretical, I call them the true, quote, true probabilities, and these experimental or empirical probabilities. So don't mix those up. Okay, fantastic. Let's see. What else do people say? This one, 2 out of 2 to the 10. Very nice answer because it has 2 to the 10. And this one is ever so close to being perfectly correct, but is not quite right. But this person probably knew what was going on and was just a little bit sleepy. Let's see if there's other ones. I don't know. D&E, very good. The correct answer was gotten by 11 people. It is 1 out of 1,024, also known as 1 over 2 to the 10. And the reason is, when p equals 0.5, we're counting the number of ways you can get to 0, and then we're multiplying it by the probability of each way. Now, the number of ways you can get to 0, there's only one way. You have to go left, 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 left. It's the sequence of all lefts. Last time we were thinking about it as a monkey typing on a typewriter. The most extreme situations only ever have one way to do it, because you have to have exactly the sequence of every single thing is L, or every single thing is R. There's only one possible way the ball can get to 0. It has to go skirt along the outside, left, 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 and then land there. In contrast, number 5, like we talked about in the middle, there are many ways to get there. You could go right and then left. You could go left, right, left, right, left, right, left, right, left, right, and go there. You could go down here, over here, down here. There's lots and lots of ways to get to 5, which is why we're seeing so many 5s. There's just more ways to get to 5. The individual probabilities are also easy to calculate. They are p and 1 minus p, powers of p and 1 minus p. In this case, p is 0.5, so it's just powers of p. There's 10 layers, so you have to get 10 things in a row, right? So it's 0.5 to the power 10, also known as 1 over 2 to the 10. 2 to the 10, as every good computer gamer knows, is 1,024. Very common number in computers, because computers have little 2-fingered gnomes that live inside them. And when 10 of them get together, they make a 1,024. Okay, let me see. Were there any other interesting wrong answers? I guess there were lots of guesses. Oh, this 826 over 1,024, that might be the middle number or something. So if 826 is some like 10 choose 5, that would be like the middle number. And same with 1 out of 512 and 2 out of 1,024 is like the probability to get 0 or 10. So maybe some people mixed up the question. But that's a nice warm-up question. Any other questions or comments about this warm-up problem? So the thing we are going to show you today is not only can you sort of do it by hand, and in this case it's p to the power 10. It's not so bad. You can also use a calculator. So last class we mentioned this thing from stattrek, not to be confused with Star Trek. And I have lost my mouse once again. Oh, yes. Yes. Please. Is the question, where is the mouse?
In that case, it looked like the probability of getting 0 and the probability of getting a 10 were the same.
Yes. In this case, they are.
So would that hold for any binomial distribution? Would that always hold for any binomial distribution?
Well, let's think about why is it true that they were the same. Does anyone have a good reason to say why the bin of getting a 0 and the bin of getting a 10 were equally likely in this situation? Yeah. Yeah. There's only one sequence for both. There's only one sequence for both is absolutely true. So the number, you can really think of the binomial probabilities as having two parts, right? There's the number in the front, and the number in the front is 1 for both. But there is another part of the binomial distribution, which is the p to the power stuff, q to the power stuff. P to the power x, q to the power n minus x. And in this particular situation, not only do the ones work out the same, but the p to the power x and the q to the power n minus x, those also worked out to be the same. So you're half right. Does anyone have an idea for the other half of the sort of equation? So yeah, let me write this on the board. So the binomial probability that we're doing is n choose x, p to the power x, q to the power n minus x. This one is always symmetric. Always symmetric. And that is because if you have n things, you choose x of them. Let's write it up here. N things, choose x of them. You can also choose n minus x of them. If you have n red balls and you're going to choose x of them, you can choose the ones you're not going to choose, n minus x of them, throw those ones away, and then you're left with the x. This is always true. You can also check it by the formula. So the first bit is always symmetric. This is always symmetric. But what about this one? Question mark? Is that symmetric? If you flip x with n minus x, does this stay the same? Yeah. It looks like it. Let's do it. Let's flip. Yes, so it's symmetric in a certain sense in that it flips the p and the q. So when you have a binomial with n things and a p, that will be the same as the binomial flipped with the q. So maybe we can write this as a little statement. So if this gets flipped to n choose n minus x, p to the n minus x, I'm running out of room here, q to the x. And so what is the conclusion? Is that because of this, the way I would write this as a random variable, a binomial with n things and p is equal to n minus a binomial with n things and q. So in other words, there is a symmetry in the binomial between left and right, but in the symmetry, you have to also swap the p with the q. You have to swap the p with the q. In this particular situation, it looks perfectly symmetric because p is 0.5, q is 0.5. So when you swap them, it's still symmetric. In general, you have to swap them like this. This one is really, you could think of this as counting the number of successes. This is counting the number of failures. And then you do n minus the number of failures. You get the number of successes. So this is how I would think about it. Maybe you have a different way. Do you have a different way of thinking about it?
No, it's good. It's good. Key thing is that the probability x equals 0 is equal to the probability x equals 10 there, if and only if p equals a half. In other words, p equals q equals a half. Now, what happens if p was, say, 0.9? 0.9, what would be the probability x equals 0 versus x equals 10?
Yeah, this is where I like to use my sort of intuition. I try to think of which one is bigger. Right?
It is.
I have a 90% chance of getting a success, or if you want, a 90% chance of going right. Am I more likely to end up at 10 or more likely to end up at 0?
Right.
Well, and it seems intuitive that if you're kind of biased in that direction, the 10 should be more likely than the 0. And indeed, if you work out the math, it will work out that way as well.
So we can simplify things a bit because the n choose x is always going to be 1. And then you can think about the p to the x, q to the n minus x. But the point is when x equals 0, that's simply going to sum to p to the n. So you're simply comparing, and when, so it's going to be p to the n for x equals 10. It's just going to simplify to q to the n. So the probability x equals 0 simply says if p equals 0.9 is the probability of a success. What are we saying? Well, we're saying we got 10 failures in a row. So that's q to the 10. So that would be 0.1 to the 10th power, whereas the probability of getting 10 successes in a row would be 0.9 to the 10th power. You can compare your 0.1 to the 10th power and your 0.9 to the 10th power, and these are drastically different numbers.
Yeah, very nice. Let's do it also with the,
Then my
calculator here.
calculator would be my friend if I'd remembered to bring my calculator.
Well, fortunately, we have the power of the internet. Actually, we don't have the power of the mouse. Where did the mouse go again? Yes, we're struggling with the mouse today. Okay. Yes. You know, Guelph is well known for its veterinary school, so maybe they can help us out with this. Where is this goddamn thing? Okay. See, now it's on this screen, and then I move it over. Okay, now it's here. Okay, we found him. Okay. So here is from stattrek. This is the binomial calculator, and you tell it what you would like to calculate. You can either tell it, I want to know the probability of an exact value, or I want to know all the probabilities in some interval. And then you have to fill in these numbers. So the probability of success on a trial, this is where you have to use your human brain and know that that's the p-value. That's p at 0.5. Yeah, p is used a lot, so sometimes p means different things. In this case, p is the probability of the trial. And the number of trials, that's what we called n. That's 10. And then the number of successes, this is what we're trying to calculate, that was 0. So if you put in 0.5, 10, and 0, that will, in this little box over here, should pop up the answer from the morning warm-up. If I hit calculator, it calculates it. Okay, look at this. It says 0.001. Is that what we did earlier? I said it was 1 out of 1,024. Is that exactly equal to 1 out of 1,024? Well, not really. Close, though. The computer is rounding it off. So you're going to get some rounded answers, which is very nice. And in fact, they've drawn all the values over here for you for the different numbers, 0 to 10. And you can see 0 and 10 are equal. And they're both just a hair under 1/1000th. Very nice. So this is how you would do it with a calculator. On your homework, not the one due this week, but the one due next week, we'll have some like this, where you have to use the calculator, because they're just some crazy big numbers. So you can either sit there with a calculator and calculate and add them all up, or you can just put it in this online calculator and be able to use it.
So let's give it 10 successes now.
Ooh, 10. Okay, let's put in 10. All right, 10. So I'm changing x to 10. And if I run it, probably not much will change. Calculate. Okay, not much changed for the probability x equals 10. These other things got filled in very nicely. It gives you the probability you're less than 10, or the probability you're less than or equal to 10. You might be interested in those in some
let's go up to the probabilities again. Oh, you did 0.5, but we were asking about 0.9.
Ah, should we do 0.9 as well? Okay, let's do 0.9.
Yeah, let's do 0.9.
0.9, and now let's compare it. So if I do 0.9, and we hit calculate, then now the probability you're equal to 10 is a whopping 35%. So if you have a 90% chance of going right at every juncture, you have the probability of getting a sequence of right every single time, 35%. And you can compare on this little table over here. Oh, this only starts at 4 for some reason. Interesting. Okay.
Okay, let's do
0.
The 0, yeah.
What's the chance of getting all left? That must be some incredibly tiny number. Let's find out. Ah, it says the probability is 0. Wow. So you have a 90% chance of going right and a 10% chance of going left. What's the probability you get 10 lefts in a row? The computer says it is 0. Is it actually 0? Yeah. It's 1 over 10 to the 10, so it's 0.000000 with 10 zeros total, and the computer has rounded that off to 0. So you got to be careful with these things. The computer will sometimes round, and you should be aware of that. But this is correct to 3 decimal places or something?
4 decimal places.
4 decimal places. Yeah, that's good to know. In real life, usually 4 decimal places is plenty. So if you're in pure math class, be careful. The probability is not actually 0, even though it says 0.
So while you've got your stattrek up there, let's solve this one.
Let's solve this one. Okay.
Let's solve this one.
Let's put it on here so we can know what is this one.
Just that from current slide. Let me see if I get this to show up nicely, more or less.
Yeah, I think you just got to hit. Yeah, you're good. You just got to hit forward
Where?
a little bit. Oh,
We're
okay.
good. Got it? This we've got to go forward. Yes, got to go forward.
Okay. So n equals 10.
Oh, go there.
And
Yep.
p equals 0.5. And now we want to know all these different things about 4. Less than or equal to 4, equal to 4, greater than or equal to 4. Why are we so obsessed with all these different things? Well, in real life, you often care about less than or equal to things. So you like win a prize if you get 4 or more correct answers. You take a wrong turn if there's 4 or more errors. So this is the kind of thing we're interested in. Hopefully you know what these symbols mean from your calculus class or any other place where you learn this kind of thing. Let's put it in the stattrek calculator and see what the answers are. So I still have 10 and 0.5. And now I'm looking at x equals 4 is the magical number that I care about. And if I hit calculate, then I get all these numbers. So the probability it's equal to 4, 20%. The probability it's strictly less than 4 is 17%. What's the probability it's less than or equal to 4? Well, actually, 37%. You might notice is the sum of these two numbers. That is on your first homework. If it's less than or equal to 4, it can either be less than 4 or equal to 4. This is the kind of thing we did before the midterm, and you can add them together. 62% chance of being greater than 4. Hey, that's the sort of complement of this one, less than or equal to 4. You're either less than or equal to 4 or greater than 4. So these two together have to add up to 100%. And once again, what's the difference between greater than 4 and greater than or equal to 4? 62% versus 82%. The difference is the probability you're equal to 4, 20%. So all these numbers are really containing two pieces of information, the less than 4 and the equal 4, and you can combine them in all sorts of ways to get all these things. This is a skill you will get good at by doing lots of practice. I think we have nailed this problem using the stattrek calculator. It's too easy with the stattrek calculator. Let's find a more difficult way to do it.
Well, more difficult way. I won't say more difficult, but it will give us more options. A couple other things to point out. We talked about the expected value very briefly, that the so-called mean or expected value, you flip the coin, it's a fair coin, you flip it 10 times. On average, we're going to expect to get half heads and half tails. So the expected number of successes is 5. Okay, the discussion of expected values is to come yet. And then there's something here called the standard deviation. And we will get to that too. This is going to be a measure of variability in our outcomes, possible outcomes. Okay, so we've gone through the stattrek business. And I'll say one other thing there. When you get practice problems, watch very carefully on when you do these problems, whether it says at least, no more than, because people mix up the words fairly frequently where they aren't sure whether the equality is included or not included. So if I say more than 4, is 4 included? No, it is not. If it says at least 4, is 4 included? Yes, it is. So you got to kind of watch those very kind of carefully there. Okay, so what did we want to do? We looked at the stattrek calculator. And now we're going to discuss R functions for probability distribution. So we got a slide here which is kind of painful at the start, but it becomes a useful reference to you in the future. So we've got 4 key functions in R for binomial distributions, and there's all kinds of other functions for other kinds of distributions. We basically call them the D functions, the P functions, the Q functions, and the R functions. And we're going to ignore the Q functions for now. We're going to make use of those when we really get to continuous distributions. For binomial distribution, you combine each of the letters D, P, Q, and R with binom for short form for binomial. Okay, so we've got a D binom, P binom, R binom to sort out here. And again, these things exist for a very wide range of special probability distributions. So the first one to know is that for a discrete random variable x, of which the binomial distribution is a discrete random variable x. Why do we call it discrete? Because x takes on particular integer values, in this case, non-negative integer values of 0, 1, 2, and so on up to whatever our value of n is. And so what this is going to return for us is an individual probability for a given value of x. In other words, the probability that x takes on the value of x. And the p function is a cumulative probability. Now, do I wish that they had picked other letters to start these things? I would have preferred that they had used the p for the individual probabilities and maybe something like a c for cumulative probability, but that's not what they did. So I can't change what they did. Okay, so we sometimes just have to accept that this is how it was programmed, and whether we like the letters they picked, it is the letters they picked. That's all there is to it.
D stands for density, right?
Density,
which we'll learn about later.
Which
Okay,
has
that's confusing.
kind of a rough aspect for
Okay,
the
well, what does
discrete
P stand for?
distribution.
I guess P stands for probabilities. They're all probabilities.
Well, it stands for cumulative probability, and that's where that's kind of,
Yes, that's a little silly.
it's a little silly.
Yeah, this is a problem in probability. Everything starts with P. Okay.
Everything starts with P, yes. Okay, and then we are going to have the R function. The R functions are like, they're so cool because we can use these to do massive simulations and generate random values of x for whatever distribution is specified. So let's just go to R for the moment. And let me see. What do I want to do? Where am I? I'm on HDMI laptop. Just a second. I gotta just. Okay. Actually, I'll do it this way. Okay. Yeah. So I'm going to go through some slides, then I'll go to R, just go over them again directly in R. So here's some examples. You can just double check yourself with R. How many people have successfully installed R? A lot. So has anybody tried it and had no luck? Anybody at that point? Okay, we should be able to straighten you out in like, well, maybe fractions of a minute. Something like that. Well, maybe more than a minute, but not much longer. Okay. Anyhow, if you haven't installed R, install R. It'll be good. And then you can test these ones out for yourself on your computer. So let's use dbinom. And so here's its syntax. And again, this is the way the R documentation explains things, and sometimes they use something that we wish they used something different, okay? Okay, so for a particular value, x, what size are we looking at? That's what our n value is. That's the number of trials. And then prob equals is the probability of a success. And you can verify this using the probability mass function. In fact, we've worked this one out already with stattrek there. So if we ask dbinom 4, size equals 10, probability equals 0.5, it returns us, look at there, it gives us extra decimal places to 7 decimal places, 0.2050781. Stattrek gave us 0.2051.
No, it looks like it gave us 1.
Pardon?
It looks like it gave us 1.
What do you mean?
There's a big 1 in brackets at the beginning. What does that mean?
Oh, okay. So these ones that get put in automatically is just the line of output that it gives. Because sometimes you ask for something that's got multiple lines of output. Okay. And we don't actually need to write the size equals prob equals thing in there if we did this. As long as you know that it is x, n, and p, it'll give you
will it complain if you swap them, or will it just like give you 0?
It'll give you crap if you swap them.
So you won't know you've made a mistake.
Well, we can give it a try. Once we go to R.
Yeah. Is there a question here in the front? Yeah. So you have to, yeah, if you type in D binom, open bracket, and then all this stuff.
Yeah,
you hit enter. We're going to do it in a sec.
I'm going to type it directly in there, but we'll just kind of go through the D binom. And then if we did P binom, putting in the same things, again, it asks for X, the size, which is the number of trials, so the probability is the P value. And we put these in. And there's a probability. We've got a couple other things here to show you in a moment. Again, I don't need to actually write the size equals and prob equals thing. And what else can we say? Well, we'll just emphasize that this is not given us, so this is a common error, and I think it's a particularly easy to make common error because it uses P for cumulative probability. You see P binom, but this is not the probability X equals 4. It's the probability that X is less than or equal to 4. So we just got to keep that straight. Make sure you put that on your crib sheet. Like, honestly, we don't want people getting this wrong, of which people will get it wrong, but we don't want you to get it wrong. We don't want you to get anything wrong. We want you to get everything right. Okay. And then let's just try our binom. We're going to play with this a little bit on the...
Wait, now there's an N and a size.
Oh, this is a
now
nasty...
I'm very confused.
This is very confusing.
Oh, my goodness.
And that is the way they specify their context. So notice the potential confusion between two uses of N. The N that they are specifying here is not the number of trials, but rather how many values do you wish to simulate? How many different trials do you want to, or sets of trials do you want to make? So we'll look at that in a moment, but here's a couple of examples. If I say R binom, N equals 6, size equals 10, probability equals 0.5, this is equivalent to flipping a coin 10 times and counting the number of successes, but I'm flipping the coin not just one time of 10 times, I'm going to do it 6 times. I'm going to do that 6 groups of 10 flips.
So in other words, the N is the number of balls you drop, and then the size is how many layers each ball has to go through. Is that right?
Number of balls we drop.
Yeah, you see, here was 826. Would that be N equals 826? So we dropped 826 balls. Maybe not. Maybe I'm mixing it up.
Yeah, it is.
It is okay. And the 10 is the layers. You see, there's two things: the number of balls and the number of layers. Don't mix them up.
Yeah.
Okay. Very good.
Yeah, that is. So
I have to put your.
Oh.
Okay, we're back.
So if anybody's checking this along with R, anybody working on R right now? Just double checking it. Okay, you got that. And did you get the same numbers as me? Yeah. You did. That frightens me.
Well, not for this one.
Okay. Anybody get the same numbers as me? Am I the only one who knows how to do this? How come it works for me?
No, you must have done it wrong, Gary.
I mean, those are good numbers. I know those are good numbers. Did you get different numbers? Anybody get different numbers? What did you get? Oh, you're downloading R. That doesn't. That's a different matter. Okay, what numbers did you get? It's poofed. So typically, wherever you've downloaded things, do they go into your download file? It vanished out of your download file, so you may have put it somewhere else. That one you'll have to straighten out later. Okay. Did anybody else get a sequence? Did you get a sequence this time?
I got 7, 6, 4, 7, 6, 7.
Oh, but those are different numbers than mine. Why?
The
because they're picking random numbers. So we're not going to get the same random numbers, except by true fluke. Okay, so there's the same thing, 610, 0.5. Again, this time I get different numbers because, again, it's generating these randomly. Okay, so let's see. What else do we want to do next? We should recognize that we're not going to get the same values. So now we'll just take a look at, let's just take a look at something. Let's see, do I want to leave this right away? Yes, I do, I think so. Just a sec, I want to go to, don't want to go there yet. So, what do I want to do? I want to do this. I want to do this. I want to go to my R. There's my R. And let's go see what happens when I put this on.
You might
It's good there.
You might remember these calculations from last class. 6 plus 8. Exciting stuff. You tell your parents you went to university to learn 6 plus 8.
Yeah, exactly.
Actually, you didn't even learn it. You just had the computer do it.
Yeah, exactly.
All right, real.
So
real
yeah,
fancy.
we did some things with the d-binom. D-binom. Is that font kind of small?
Yeah, can you zoom in? Or?
Well, the other thing I can do is let's go to edit.
Well, okay, maybe while you're doing that, let me show. There's a fancy way you can get R to work on the internet. So this is called Google Colab, and they let you run programs in your browser. The secret to using Google Colab is you have to go to runtime, and you have to hit change runtime type, because it's normally Python. But if you set it to R, it will work R, which is lovely. And then you can do all your commands in here. So there's my R binom, and you see if I got 4, 5, 5, 7, 6. But if I run it again, I hit this play button to run it again. I get new numbers every time. So it's like rolling dice over and over again. That's very lovely. And we can do all the D binomes. This one, you can also do some AI stuff, but watch out because sometimes it lies to you. N equals 6, size equals 10, p equals 0.5. Wait, that's not n, that's x. Okay, I want x equals, we'll do 4. This is, All right, there you know. This is the command you were trying to run, right?
Yeah, it's the command I was trying to run.
Very nice.
Okay, we got that.
Let's go back to the little thingy over here.
Okay, so we can take a look at that. I don't want to do the p binom. P binom. Let me try something else here.
Well, that's not a number.
Oh, I know.
Oh my goodness. What happened? 0:10. I don't think that's allowed. That's some kind of illegal action.
This is the problem when you increase your font size, it goes off the screen. Okay, so what did I just do with the 0 to 10? I replaced the asking for a single value of x is I said calculate it for every value of x between 0 and 10. Okay, and so we can go across and read this and say this is the probability x equals 0, the probability x equals 1, the probability x equals 2, and so on. Okay.
That x equals 0 number, is that just a hair
second.
smaller?
That's p binom. No, this is not the probability x equals 0, the probability x equals 1, the probability x equals 2. Ooh.
Classic.
Oh,
Classic mistake.
Okay, let's go back to the d binom and give it 0 to 10. Okay.
Hey, the first one was the same. That's nice.
Yes, the first one's the same.
Just a hair under 1 over 1,000. 1 over 1,024, some might say.
This one here is the probability x equals 0. This is the probability that x is less than or equal to 0, but if it's less than or equal to 0, the only thing it can be is x equals 0. This is the probability x equals 1. This is the probability x is less than or equal to 1. So how do we get this one from this one? We add those two, right? Probability x equals 2, 0.0439 something. This is the probability x is less than or equal to 2. Where does this come from? That is the sum of this one, the probability x equals 0, plus the probability x equals 1, plus the probability x equals 2. Okay? So you can see how it's the p binomial function is cumulating the individual probabilities. Any questions on that? Okay, make sure you see it right now. Like, don't say, you know, okay, I'm going to have to study this when I get out of class. What we want you to do is have it locked into your head right at the very moment. Are you feeling it's locked into your head? No?
There's too many numbers. We need a picture. Let's draw a picture. I want a picture of these numbers.
And you want to have a picture of those
Can we
numbers.
do a picture? Can we draw pictures in R?
We can.
Let's do.
How
Let's
to
draw a
get
picture.
the best picture on this one is not a...
I asked the AI to draw a picture. Let's see what Mr.
Okay.
Google said. I'm running it. I'm doing whatever the AI says. Be careful. Okay, here's what the AI said when I asked the AI to draw a picture. I have no idea what it did. Let's see. Oh, this is beautiful. Number of successes, 0 to 10. What did it do? Let's see what it did. It did a D binomial. D binomial, is that the cumulative one or is that the probabilities one?
The D binomial is the individual ones.
Oh, look, they left us a nice comment. They said, calculate the probability mass function. Okay, that's what we want. Okay, that's the probability of each one. Probabilities and their actual probabilities. Yeah, let's accept this. Can you go away now, Mr. AI? If I thumbs up you, will you leave? Okay, I got to zoom out so that goes away. Okay, then it says plot it, and then it plotted it. Okay, that's very nice. Well, let's see what it would look like if instead of D binomial, we just do the exact same thing, but with P binomial. Let's see, we place the D, change one letter to a P, and this is not the probability mass function anymore, and this is the cumulative, in all caps, function. Okay, very nice. And then now I'm going to do it. It's not the number of successes probability. This is the cumulative probability. So there we go. Cumulative probability. All right, we run that. There we go. So that's the D binomial. Wait, no, this is the P binomial. P binomial going up. The numbers start at 0 and they get closer and closer to 1. Whereas the P binomial, the D binomial, I keep getting them mixed up. We gotta write it somewhere. Okay, we gotta write main equals. This one is D binomial. Let's put it in the title. And then this one is P binomial. Then there will be no confusion.
Well,
okay,
I'd say there's confusion because of the way they defined these things.
Yes,
like
okay.
what they used as their
this is
letters.
good. We're learning. Okay, so this one is the P binomial from 0 to 1, cumulative. And then this one is the D binomial, the going up and then down. These are the probabilities of the individual events. You see they're like 20%, whereas this one is going from 0 to 100%. Very nice. Very nice stuff. Okay, so but the real question, can I make this go away? Apparently not. I don't know. I don't know what happened. Okay. All right. So there you go. If you want to do it in Google, you can get these kinds of graphs, and you can not mix up P binomial and D binomial, or maybe mix them up less. Depends if you like pictures like me.
And you know what? I have to switch this back to 14 point.
Oh, is the font is no good? Yes.
It's driving me
Yes, this
nuts.
is a nice thing about doing it in the browser. You can zoom in and out
Yeah.
at will. Okay. Any questions or comments? Yeah. Yes. D binomial is the probability of individual events. P binomial is the cumulative probability. So it's this one in the little pictures that goes. It starts at 0 and it ends at 100. What's the probability you're less than or equal to 10? It's 100%. What's the probability you're less than or equal to 0? It's 0%. So it's the cumulative probability, the thing we called F, capital F, many classes ago. And it's related. What is the difference between these things and these things? If you add these up, if you do 0 plus 1 plus 2, then you will get the value of this one at 2, right? So if you add these up, 0 plus this number plus that number, you will get the cumulative number, this little guy over here. So one of them is the added up version of the other one. Okay. Yeah, great question. It is hard in R because the letters are a little bit silly. I guess you got to come up with a good mnemonic to remember which one's which.
Yeah, I guess the basic thing is no matter what software program is or you're working with, they will define some things in ways that don't intuitively make sense to you, and you just have to live with it. And
Well, this is why we give you
remember
a
things.
formula sheet. Make sure you write it down the right way on your formula sheet for
Yeah.
the exam. Okay.
Okay.
All right, we're back to the R.
Yeah,
The
we're back
classic
to that.
R
Back
in
to the
the,
classic R. And
out of the browser.
here's something. If you want to rerun a command, or you type something wrong, and it comes back and you've got an error,
Yeah, can you go back and change something, or
you
is
can
once
go
it's
back. So, for
once it's
example,
written, is it written?
I can just go up the up arrows, and it'll go back
Oh,
to.
you press the up arrow. Okay.
I do the up arrow, and there's.
But like, for
the
example,
binomial.
can you go to this one and edit that 10 to be an 11 and run it again, or
We
is
can
that
do that.
impossible?
Which one do you want? P binomial.
I don't want a new one that looks the same and is different. I want to change the one that was already written, or is that one written in stone?
It's already written. So
Okay, so it's like a you go to the store and they have like a little roll of tape with all your things. Once it's written down here, it's written forever. You can't change any of these. But if you press up, you will get back. You press the up arrow, you can recover one of these and then change it and run it again.
So let's just change this one to
8.
n equals 8. Trials. Okay, do it all the values. Let's just change our p from 0.5 to 0.6. Sure. And there they are. Okay.
Some numbers.
Again, so these are cumulative probabilities, and suppose I want the individual probabilities, I'll just do that same thing and change that to a D. And again, just get the relationship, okay? Always just go back and just spend a little time after just to make sure you recognize the difference between the P binomial and the D binomial and how you get the P binomial from the D binomial, okay? Again, the x equals 0 part is the same as x is less than or equal to 0, but the probability x is less than or equal to 1 is the probability x equals 0 plus the probability x equals 1, and so on. So the P binomial is accumulating probabilities. Of course, by the time you get up to the value of n itself, you have to have accumulated all the probabilities. So this one's always going to, the cumulative probability is always going to end with a 1 at the value of n. Okay, so we did that, and now, you asked a question about what happens if we mess up some stuff. Well, let's do a mess up here. Let's suppose I got my number of trials and the value of x I wanted backwards. Let's see. No, that's not what I'm going to do. I'm going to do, let's suppose I put 8 and 4, and I did that, and it comes back and
okay.
says,
100%. Yeah.
100%.
Yes.
Right.
Okay. So be careful. Don't mix them up because it won't warn you. It won't say, hey, this is crazy. You did something weird. It'll just tell you some nonsense answer. Okay, great.
Okay, so
Fantastic.
back to the R binomial.
Ooh, R binomial.
R binomial. So R binomial is the great fun one. We're going to do R binomial. We did one before with 6, but is 6 sufficiently adequate? Let's do 10. Let's do 0.5. Okay, this is flipping a coin 10 times here, and we got 5 heads. We flipped it another 10 coins, got 6 heads, and so on. Well, we can actually do this a lot, and this is going to be, we still got 2 minutes. Okay, people, you will demand a refund of your tuition fees if we end early. So what if I went to 100,000? Holy crap, that's a...
You can't flip that many coins. That'll take all day. Wah!
Whoa!
Look, I love this. The row 99,970. Yeah, all right. This is great.
Okay.
You wanted a lot of random numbers.
We're going to do something with that next day.
Yeah,
Okay.
actually, I had the AI. I was like, please draw a little picture for me. So here are 826 samples from the R binom. So I did R binom, n equals 826, just like we had at the very start of class at the warm-up. And here is the graph that it came up with. Notice it's 0 at 0 and 10 again. We didn't get any outcomes that came out 0 and 10. We would have to do even more samples. Let's bump it up. 826. That's for children. How about 826,000? All right, and now look, we're starting to have a little tiny bit over here and there. Now it's quite close. The sample size is so big that it's getting better. Oh, we gotta maybe fix the label as well. Okay. Is that all we have to say about the
That's
binomial?
all we have to say for now.
Okay.
For now.
Wonderful.
Okay.
We'll see everyone on Friday.